Good day, everyone. Welcome back. It's been a minute. You may have or may not have noticed that I have seemingly vanished from the face of the earth. I'm back with a bunch of random garbage. So, as of the past almost month at this point, I've been working on a new planet generation system for Endless Abyss. And at the moment, I'm taking the Marching Cubes approach. I'm documenting my progress over Milanote, Github, and a few other places. You can find all those links in the Discord or in the description. And so this is just going to be a quick video going over the basics of how I set up this implementation, how it works, the many, many problems with it, and how I would like to look to improve it. So to start off, it's pretty clearly Marching Cubes. If you don't know what Marching Cubes is, I'm not the person to explain this to you. Look up Sebastian Lake's video on it. It's absolutely amazing. We use this horrendous table of indices, which is called the triangulation table, that someone else made. I'm not making it myself, because fuck that shit. To turn that into this with a shit ton of other math. So, at the moment, it's kind of slow. You can see it takes if you look down here, you can see it takes about an average of 6 to 7 frames to generate each, every time we try and regenerate the mesh, which is around I'd say it's about 120 milliseconds average, give or take. And this is because there's a lot of math that has to be done here. We have to loop over, so there are 64 chunks. Each chunk has 10 to the 3 voxels in it. That's 10 to the 3. I can't do math. So 10 to the 3 times 64. That's a lot of voxels. And each one of those is a non-trivial amount of math. Now, in order to speed this up, though, originally in the older versions of this, it was a full, maybe a minute to generate a mesh like this. Now it's less than, it's like maybe a tenth of a second, which is still pretty shit. But the reason for this is massive performance improvement is this. This is, well, it might look scary, and by God, it really is. This is a compute shader, a GLSL file. So basically what a compute shader is it's code that you run on the GPU. The GPU versus the CPU, there's a big difference between the two. The CPU is really good at running singular tasks stupid fast, and the GPU is good at running a billion tasks all at once. Yeah, the CPU can do multi-threading, which is what running multiple tasks at once is called, but nowhere near as well as the GPU can do it. And so what we do, because we have 10 billion things we need to do all at once with all these voxels, we send it to the GPU with this abomination of a script. It's not actually that bad. This one's actually pretty elegant, mostly because it isn't my code, but okay, no, that is kind of a lie. It is 95% my code. It's just these functions up here aren't mine. Yeah, it's a little jank, but effectively what we do is Godot has built-in support for compute shaders. Unfortunately, it is so horrendously documented, it's actually insane. I'll probably make a video at some point making a better tutorial for it. But the gist of it is, we take our shader file, which is a GLSL file, which is not the standard GD script or GD shader system. It's a GLSL, it's a shader format. You can look it up in your own time. Effectively, in order to do the compute shader, we make a copy of our virtual GPU, if that makes any sense. We compile our GLSL shader, throw it into there, and then create a couple things called buffers. Buffers are effectively ways for the CPU to communicate with the GPU, and the problem with that is when the CPU and GPU communicate, the computer fucking shits itself and dies. And that's because when you have to communicate between the CPU and GPU, you have to wait for them to sync up. Now, normally, at least as far as I know, the GPU and CPU operate in lockstep, meaning that they both try and update at the same time. Unfortunately, this is pretty inconsistent, and as you can see here, the GPU is taking about 6 milliseconds to process, and the CPU is taking about less than 1 millisecond to process, which effectively means they're not in lockstep. Okay, I don't know what I'm talking about, but basically, when we transfer data between the CPU and the GPU, we have to wait for one of them to finish, and that is horrendously slow. You might notice the GPU is taking exponentially longer than the CPU to process, like I just said. Well, every time we want to send data from the GPU to the CPU, we have to wait this amount of milliseconds, which is a huge downside, because that means we cannot, at least as far as I know, we cannot get the time to generate lower than whatever our average frame time is. Which sucks absolute big fat fucking gorilla dick, but hey, what are you going to do? I might be wrong on that one. People who have more knowledge on GPU architectures, fact check me please, but as far as I know, that's the issue. Which seems incorrect now that I'm thinking about it, because I've had much higher update speeds. Anyways, regardless, basically, in order to transfer data between the two, it's very slow. And so we want to transfer as little data as possible. And the data that we do transfer is literally the stuff we send to the GPU is one buffer that contains a bunch of parameters, like our ISO value, our noise scale, and a couple other random things. We also send it, well, this counter buffer, this one's a bit of a weird one. We're not exactly sending it, it's more so kept between each iteration. Because when each thread of the GPU is all running in parallel, if you've ever worked with threaded or parallel processing, you'll know if two things try to access the same memory at once, you start having some major problems. And so this counter buffer is there to help prevent that. And then we have this try buffer, which is where the GPU writes the mesh data to, for our CPU to read that and then turn it into this scuffed ass FBM mesh. And yeah, so it's a lot of jank. Once we receive all that data, we go ahead into this process output function and use a thing called surface tool, which is a Godot thing that is exactly what it sounds like. It's a helper tool to create geometry. Basically, this is just allows me to skip the actually not that bad pain of indexing and generating normals for the mesh, which in hindsight I probably should just opt to do this manually without using surface tool, because it's way slower to do it this way. But basically, we go through, we append all the vertexes and set their normals. Normals are calculated in the shader by doing scary math. Vector math is confusing, but I'm actually learning it, so hey, would you look at that? Spooky, I know, yeah, excuse me. Anyways, then we index it, which basically merges nearby vertices. It doesn't fucking work. And a couple other random things, and then we generate the closure mesh and make this shit, and yeah, incredible, amazing, I know. So, one thing to keep in mind, though, is if I went and profiled this right now, you'd see that this process output function is taking about, like, I'd say a third of our processing time, which is a pretty huge amount, to be honest. Unfortunately, we can't exactly make the mesh in the GPU, because we can only transfer raw bytes between the two. Like, as much as I would love to transfer just mesh data outright, it's probably possible, but I'm not familiar enough with the data structures to do it at the moment, but I might figure that out. Anyways, so that gives us this. And so you might be wondering, you're probably not, you've probably already clicked off this video, it's going to be long and a lot of ranting, but anyways, you're probably wondering how the fuck do we get this weird ass shape? Well, this is a combination of two things: simplex, noise, and fractal Brownian motion. Simplex noise is effectively just fancy fucking, I don't know if you've ever heard of a noise function, it's that, but like, what the fuck? I've never actually taken a look at this function, that is weird. Anyways, I stole this from a shader toy thing, you can see it right here, and on the GitHub you can find it in the shader file. And then we use fractal Brownian motion, which is effectively a way to simulate, it's just Brownian motion, which is like the way that fluids function and voids function and other shit, but we do it as a fractal, and so it's self-similar. If that makes any sense to you, then congratulations, you're a nerd, but also probably really fucking smart, and probably have like a job in computer science or some shit. Congratulations. Anyways, we combine the two and make trippy, weird shapes like this. Now, before, I had a system where I would use this scuffed-ass abomination to take a shader. For example, if I open up the shader graph, take this shader and rasterize it into a bunch of fucking sprites. This would give us a 64 by 64 by 64 3D texture, which I would then send to the GPU, which it would then use to create the mesh. Only problem is that is transferring a shit ton of data, A, and B, it's transferring it in the form of rasterized images. And rasterized images have a limited resolution, meaning that we got these weirdly chunky meshes that looked very, like, they did not look smooth in the slightest. You'll notice this one's pretty polygonal, that's because I have normal generation turned off. If I hit clean up mesh, now you can see smoother faces. Yeah. And so, thing with Marching Cubes is it is designed to function on a scalar field, which is basically just a function, a 3D function that returns a value. It's just a 3D function. That's all it is. And basically, it's meant to measure. Generally, you want to use it to measure distances from points, like a sine distance function. I'm pretty sure is a scalar field. And a couple other things. Lol, a noise function is a scalar field. The most important thing about these, though, is that they're not rasterized. They're not a bunch of set points. Pixels, there's a limited amount of resolution. Scalar fields have infinite resolution by nature. They're functions. If you understand what that means, yeah, congrats. You saw through my absolute dog shit explanation. But anyways, so the reason why we're doing noise on the GPU side now is not just for the stupidly shit performance impact of transferring data between the CPU and GPU, but also because it eliminates the need for the cringe-ass rasterization and this, where is it, tricubic interpolation function, which basically is just a 3D way of using interpolation in order to smooth out the pixels, which, fun fact, does not fucking work. Anyways, I've been talking way too much. So yeah, that's the Marching Cubes shit. I'm going to be working on that a lot more. You may have seen some clips of stuff I've been working on. Like, I ended up with this really cool overhang type thing. This is something you can't do with my existing planetary generation system because it only stores height values for each vertex instead of like anything else, so you can't have overhangs, and that's one of the main advantages of this. Also terraforming, but I've yet to implement that, and I have no idea how I will implement that. But anyways, this is the Millinode. Yeah, weird thing, whatever. It's like Trello, but not. Anyways, I'm storing most of my progress data here, and you can find Discord, Trello, and most importantly, the GitHub repository for this project. It's open source if you want to steal this and work on it, or just preferably don't just steal it and sell it as your own. That would kind of be sucky, and I will chase you because legal reasons. Anyways, that's all I have for compute shaders and Marching Cubes for now. Anyways, yeah, that's really about it. I might upload another video later for like some other stuff I've been working on, but overall, this is the main draw. I've been banging my head against the wall getting this to work. I will probably be... This is going to be my main project over the next, like, fucking God knows how long. And so, yeah, you'll probably see a lot of this. I do have some stuff for the game itself, though, coming out soon. And hopefully there'll be an update soon, because there's actually quite a bit that I've added that I definitely want to show off. So, yeah, that's about it for now. Thank you so much for watching. Like and subscribe. 98% of you aren't actually subscribed. I'm very tired, if you couldn't tell. Have a great day, y'all. Thank you so much for watching. Bye.